Hi, in the last video we discussed about how do we solve a pair of first order linear homogeneous equation by using eigenvalue method. So we consider the cases when the eigenvalue of the matrix A are distinct, right? So it could be real and distinct or complex. Okay, in case of the complex, the two eigenvalues are the conjugate of each other. In case of the real, we consider the three cases when both eigenvalues are positive, when both eigenvalues are negative, when one is positive and the other negative. Similarly, for the complex eigenvalues, we consider the cases when the real part of the complex eigenvalue is negative, when that is positive, or when that is zero, right? So the next thing we want to consider is if the eigenvalues of the matrix A is repeated. Okay, for example, so you are trying to solve basically x prime equals to a times x, right? So like this, but A is the matrix of the coefficient. So if the eigenvalues of A are both repeated, if eigenvalues of A are both equal, we call repeated. Okay, so how do we find out the general solution of the system of this equation, system of pair of equation, if both eigenvalues are equal, or we call repeated? Okay, so in this case there will be two cases. Okay, there will be two situations. So case one is if the matrix A is a diagonal matrix. Okay, for example, let's say A0, 0, A. So in this case, this is called the diagonal matrix, meaning the diagonal that starts from the top left hand corner to the bottom ending at the bottom right hand corner. This is called the diagonal matrix. All other elements are 0 and these diagonal elements are equal. Okay, whatever you have, they are equal to each other. So in this case, you will have two repeated eigenvalues. Both of the eigenvalues will be A and A. Okay, and then so eigenvector will be independent of each other. In this case, there will be two independent eigenvectors. The reason is whenever you try to solve AV equals to lambda v, then you will get the whole thing on the left hand side. Okay, so you will get 0 equals to 0 kind of condition. Okay, so so in that case, what you do is so you pick so both of the eigenvalues lambda 1 and lambda 2 will be the same. Okay, so in that case, so you will be free to pick the vector v. So you will pick v equals to 1. For one eigenvalue you can pick 1, 0, and for other eigenvalue you can pick 0, 1. Okay, so in this case you will get two independent eigenvectors. Okay, if you get two equal eigenvalues when the matrix A, if you get two equal eigenvalues, then there are two situations, two scenarios. One scenario is the matrix A is a diagonal matrix. In this case, you will get two for two eigenvalues, two equal eigenvalues, you will get two independent eigenvectors. So you will be free to pick. We will see an example. You will be free to pick them, and you will be picking one for one eigenvector you will be picking 1, 0, and for another eigenvector you will be picking 0, 1. Okay, that's what you will be doing. But in the case 2, the A will not be a diagonal matrix A, B, C, D. It will be like this. In this case, let's say if lambda 1 and lambda 2 are equal, we get the repeated eigenvalues, right? Equal, then you get only one eigenvector, right? Eigenvector. So you find out that eigenvector by doing AV equals to lambda v. You find out that. But to find out the fundamental set of solution, you will need two eigenvectors. You will need two solutions, because one of the solution you will be doing e to the lambda t and then v, right? So for the another solution, what you will be doing is, So what you will be doing for the other case, this is vector x. So what you will be doing here is you will try to find out a vector w. This is one solution, right? We need to find out another solution to find out the general solution, because general solution needs two solutions, right? And then for the next solution will be of the form, will be in the form of x equals to t e to the lambda t, and then v, vector v, okay, t e to the lambda t vector v plus e to the lambda t vector w. This will be the second solution, okay? So where w is obtained from a minus lambda I times w equals to v. So v is the one that we got from here, okay? So you will be solving this equation to find out w, okay? After you find out w, you will just plug it in here, x equals to that, okay guys? So then finally the general solution is, you get vector x equals to, this is like, let's say this is x1 and this is x2, okay? So you can write c1 x1 plus c2 x2. So this is what you will do. So basically, if the eigenvalues are repeated but the matrix A is not diagonal, it is a little bit of work, okay? But it is not bad at all. You can definitely do that. But by the way, I forgot to tell you that, so before you write the final general solution, you need to check the run skin of the two solutions, x1 and x2, okay? And you will get, usually you will get non-zero, okay? Now how do we decide the stability of the origin, okay? In case I, if lambda is less than 0, okay, then we call that 0, 0 is stable proper node. Then 0, 0 is stable proper node. If lambda is greater than 0, then 0, 0 is unstable proper node, okay? Unstable proper node. This is the case I. Now how about the case double I? So in case double I, what you get is, because in case double I, the A is non-diagonal, right? So if lambda is greater than 0, then we call, then 0, 0 is unstable proper node, okay? Unstable proper node, proper node. And if lambda is less than 0, then we call 0, 0 is improper, okay? Improper node. If lambda is less than 0, then 0, 0 is stable improper node, okay? So this is the basic steps behind the method, okay guys? So next, what I'm going to do here is I am going to take examples, all right? Let us look at this example. So here we have x1 prime equals negative x1 and x2 prime equals negative x2. These are basically, they are not connected to each other, right? You can basically solve the first one separately and second one separately and then write the solutions, right? So you can do that way. Or if you want to use the matrix method, so how do you write that? You can write this as x1 x2 prime equals to, you can write this as, let's say, -1 0 and then 0 -1 and then x1, x2, right? If you multiply this matrix, you will get negative x1, negative x2 on the right side. So what is A then? A is a diagonal matrix, right? Negative 1, 0, 0, negative 1. So how do I find out the eigenvalues? To find out the eigenvalues, we need the characteristic equation, right? Characteristic equation is lambda square, right, minus sum of those negative 2 lambda, and then plus the determinant. How much is that? 1, and minus 0, that is just 1, equals to 0, right? So you will get lambda square plus twice lambda plus 1 equals to 0. So you get lambda plus 1 square equals to 0. So you got lambda equals to negative 1 and negative 1. They are the repeated. Basically, see, in case of the diagonal matrix, the eigenvalues are those diagonal elements. If all other elements are 0, and if there is only non-zero element on the diagonal, then that will be basically the eigenvalues. Okay, so we got two repeated eigenvalues, negative 1 and negative 1. Since this matrix is a diagonal matrix, so we will get two independent eigenvector. How do I find out that? So okay, so let's do for lambda equals negative 1. For lambda equals negative 1, how do I find out the eigenvector? You do AV equals to lambda V, where V is the eigenvector that you want to find out, right? So it is negative 1, 0, 0, negative 1, right? And then V is, let's say, xy, let's say, equals to lambda is negative 1, and then xy. So if you simplify that, what do you get? Negative x equals to, let me write down negative x and the negative y, right? How? Because negative 1 times x times 0 times y is negative x. Similarly, 0 times x is 0, and then negative 1 times y is negative y. That's what you get. Okay, and then this is equals to negative x, negative y. You see that? See, now you get negative x equals negative x, and negative y equals negative y, right? So you see that everything cancels. So there is no values of x and y. So you are free to choose x and y. So let us say that vector v is, we assume that as xy. For one, let's say that this is 1, 0. Okay, so the other one will be, you need to do independent of this one. So because if you take another negative 1, you will get exactly the same condition, right? So for the next vector, you pick v equals to xy equals to, let's say, 0, 1. Okay, so what do you get then? So what is the solution? So the solution for the first eigenvalue is, so for this eigenvalue, the solution will look like x equals to e to the negative lambda t, vt, right? Vt, what do you get? You can just write v. So v, how does that look like? That looks like e to the negative, e to the lambda t, right? Not negative lambda t there. Lambda is negative 1. So negative t, negative 1 times 2 is negative t, and then 1, 0. Similarly, for this one, you will get x equals to e to the negative t, and then 0, 1. That's what you get, right? So if you find out the Wronskian of this, you will get it is non-zero. How do I find out that? Is basically you just simplify that, right? So Wronskian of x1, x2. x1, x2. Let's say this is x1 and this is x2. So what do you get? This is not square, okay? I'm just saying that x1, x2 inside the parenthesis. So this is the determinant of, it is e to the negative t, 0, because if you distribute that, and this will be 0 e to the negative t. So if you multiply that, you will get e to the negative twice t, right? Which is not equals to 0. So the fundamental set of solution, is what? The fundamental set of solution is, you can see that vector x equals to c1 e to the negative t and then 1, 0 plus c2 e to the negative t and then 0, 1. This is basically the fundamental set of solution. Okay, guys. Now, so what do you think? What will happen about the stability of the origin? Okay, if you want to check the stability of origin, as I mentioned previously, if that lambda value is positive, then it will be unstable proper node, right? since if the lambda value is negative, then it will be stable proper node. So also 0, 0 is stable proper node. Stable proper node. How do we know that it is stable? Because lambda is -1. Or you can see that if t tends to infinity, that is when t tends to infinity, then what happens? Then vector x tends to vector 0. That means 0, 0. Okay, it will go to the origin. That's why it is a stable proper node. So if you want to see how the direction field look like in this case, so the let me use that we have that slope or direction field. So in the system, what is our equation is negative x1 is negative x, and this one is negative y, right? Look at this. So if you see, if you start anywhere, it is directly going to the origin. Okay, so in this case the origin is a proper, so stable proper node, and this is also called the stable star node. Okay, this is also called the stable star node because it is like a star, so it is going to the origin. Okay guys, so this is how you solve in case of the if the coefficient matrix, that matrix A is a diagonal. So in the next example, what I'm going to do is I'm going to show you how to do the problem if the matrix A is not diagonal. Okay,